I apologize, apparently I have a 10-minute limit on these recordings. As I was saying, when we draw the px, py, and pz all together, it looks really interesting. We have this kind of flower-like shape here in the middle, where we have superimposed the s orbital, and then the px, the py, and the pz all together. And for all of that, we only need to put one more electron in there. I've already filled up 1s and 2s, so now I need to put my 2p electron. It doesn't matter which of these it goes into, I'll just place it there at the 12 o'clock position. So our electron configuration now is 1s2, 2s2, 2p1. Okay, we're ready for our next rule for how we place these electrons. And this one is called Hund's rule. So Hund's rule states that if we have a series of orbitals that are of equal energy, like in the case of all of our p orbitals, one electron must go into each orbital until all of the orbitals contain one electron, and then we can start to pair them up. So what this looks like is boron, these each represent a p orbital, px, py, pz. Boron gets one electron. In carbon, we're not going to pair up these two electrons in one orbital. Since all of these have the same energy, they want to spread out. Remember, electrons repel each other. And then in nitrogen, we continue giving one in each orbital until we get to oxygen. Now we have no choice but to pair them up. My analogy for this is what I call don't sit next to strangers on the bus. If you imagine getting onto a public bus where the seats are all in pairs, if you walk onto that bus and there's 3 sets of seats and they're all open, you sit down anywhere, it doesn't matter. Now, let's suppose you get onto that bus and in one of those pairs of seats, there's a stranger sitting there. Chances are you're going to opt to sit on your own than sitting next to the stranger. I know some of you are like super extroverted and you're like, I want to go make a new friend, and you go sit next to the stranger. But most people are a little bit more wary than that. So that's why I call this the don't sit next to strangers on the bus. Electrons don't like to be forced together, so we can't pair them up until each one is by itself first. So let's look at how this manifests for something like drawing the electron configuration of carbon. So now we have 6 electrons. I've left my picture of boron down here at the bottom. We have 6 electrons, so carbon is over here. We have one more electron to place. I've got 1, 2, 3, 4, 5 in here already. Hund's rule tells me that the second p electron can't go down here because it would be sharing the py orbital with this electron that's already there. So it has to go either in px or pz. Doesn't matter which one. It doesn't matter which side of those. I typically opt to start at one position and go either clockwise or counterclockwise. So there's my carbon picture. Now, the other thing I want you to notice when we look at our electron configuration, 1s2, 2s2, 2p2, if we regard this as the p block, we can know what the last electron piece of the electron configuration is going to be based on the position of our element. So carbon is in the second column of the p block, and it's in the second period of the periodic table, which gives us 2 because it's in the second period, p because it's in the p block, and 2 because it's in the second column of the p block. It tells us that last piece of the electron configuration based on the position on the periodic table. Okay, I think we're ready for the next rule or principle for placing electrons, and this one is kind of the more confusing one. On its surface, it seems pretty straightforward. It's called the Aufbau principle, and literally what that means is that electrons build up from lowest energy to highest energy. But where this gets really weird is, so far it's all seemed pretty straightforward. We went 1s, 2s, 2p, 3s, 3p. But if you look at the energetics, notice that 4s is slightly lower in energy than 3d. And that means that according to the Aufbau principle, the 4s subshell is going to fill before the 3d subshell. And here's another depiction of this same sort of thing. Remember that the difference in energy level is very great because of r squared, the difference in the energy as the distance goes up, is pretty big. But within each energy level, there has to be a difference between the s, the p, or the s, the p, and the d orbitals. And so basically we get to a point where when we start looking at the d and f orbitals, there's a little bit of almost overlap between the 4s and the 3d. 3d is slightly higher in energy than the 4s. 4d is slightly higher in energy than 5s, excuse me. And then when we start getting the f orbitals, they make it even more complicated. What that means then is that when we're filling orbitals, the 4s orbital must fill before the 3d orbital. And you'll notice on the periodic table, the first row of d block elements occurs in period 4 after the 4s elements. And if you look at your periodic table, we know that 3d is the first d block that we see, but the 3d orbital comes after 4s. So this is 3d, 4d, 5d, and 6d. Now, the f ones, we kind of put them down below just for convenience of drawing the periodic table. But these two rows actually belong in here between the 6s and the 5d. Conveniently, again, the periodic table can tell you a little bit about what orbitals are being filled by that element. Now, if you need a good way to remember the order in which to fill orbitals, here's a picture. We have the first energy level, there's an s orbital. Second energy level, we have 2s and 2p. Third energy level, 3s, 3p, 3d, and so on. And I even included down to the 7th energy level. I didn't include these because we don't have any elements that have electrons in them yet. The rule for filling orbitals is if you set it up like this, the orbitals fill diagonally from the top right. So first we fill 1s, then we fill 2s, and next we go 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, 5f, 6d, 7p. So we use this depiction and we fill diagonally from the top right. Okay. I want to do one more of these to practice, and then I want to have you work on your activity. So let's look at scandium. This is on the very top of the back of your activity. We're going to look at scandium. Scandium is element number 21. So if we look at this depiction, scandium is going to be right here. The reason we're looking at this one is it's the first time we start dealing with d electrons. So based on the Aufbau principle, we're going to fill 3p, and then we're going to fill 4s. So if we move across, we fill 1s, 2s, 2p, 3s, 3p, then we get down to 4s, and then we get into the d block, but we have to remember that this isn't 4d, this is 3d. So let's start drawing our picture. We've got 1s1, that's hydrogen, 1s2, that's helium, 2s1, that's lithium, 2s2, that's beryllium. Now we put in our 2p orbitals. 2p1, that's boron, 2p2, that's carbon, 2p3 is nitrogen, 2p4 is oxygen, 2p5 is fluorine, and 2p6 is neon. Next, we're up to the 3s. We put another ring. 3s1 is sodium, 3s2 is magnesium. Now's where it gets really messy. We have to draw another set of p orbitals. Notice that they lie along the same axes as the first set of p orbitals. Since these correspond to the x, y, and z axes of our atom, they have to stay lined up. So you can't just draw your next set of p orbitals wherever you want. They have to line up with the first set of p orbitals. So then we go 3p1, and that would be aluminum.